On September 29, 1957, at precisely 4:22 p.m. Moscow time, a chemical explosion destroyed one of 14 underground storage tanks at the Mayak plutonium production complex. The explosion lifted a 160-ton concrete lid, destroyed buildings 200 meters away, and released approximately 20 million curies of radioactive material across 20,000 square kilometers of Soviet territory. This was not an accident in the conventional sense. It was the inevitable result of a design philosophy that treated high-level radioactive waste storage as a secondary engineering problem rather than a primary safety concern. The technical foundation for this disaster was embedded in the Soviet Union's choice of the sodium uranyl acetate reprocessing method, a chemical pathway never adopted by Western nuclear programs. This process, developed under the extreme time pressures of the early Cold War, created waste streams with fundamentally different thermal and chemical properties than those encountered in American or British facilities. Yet the storage systems designed to contain this waste were based on conventional industrial standards rather than radiochemical-specific requirements. The Mayak complex, constructed between 1945 and 1948, using forced labor from Gulag camps and Axis prisoners of war, represented the Soviet Union's desperate attempt to close the nuclear weapons gap with the United States. Stalin had witnessed the devastation of Hiroshima and Nagasaki and understood that nuclear weapons represented not merely a new class of armament, but the foundation of post-war geopolitical power. The urgency of this mission permeated every aspect of Mayak's design and operation, creating what would later be recognized as a systematic subordination of safety engineering to production requirements. The acetate reprocessing method itself reflected this urgency. While Western facilities developed the Purex process, which separated plutonium using tributyl phosphate in a relatively stable chemical environment, Soviet engineers pursued a more direct but inherently hazardous approach. The acetate process involved dissolving irradiated reactor fuel in concentrated nitric acid, chemically altering the oxidation state of plutonium, then adding acetic acid and base to precipitate both uranium and plutonium as solid acetate salts. This method could achieve rapid plutonium separation but generated liquid waste containing high concentrations of ammonium nitrate mixed with radioactive acetate compounds, a combination that would prove chemically unstable under elevated temperatures. The storage facility constructed in 1953 to contain this high-level waste consisted of 14 stainless steel tanks mounted in concrete canyons 8.2 meters underground. Each tank could hold approximately 300 cubic meters of liquid waste, with the entire facility designed to accommodate the anticipated waste generation from plutonium production operations. The underground placement was intended to provide radiological shielding and containment in case of tank failure, but this design choice also created access limitations that would prove critical during emergency conditions. The most significant design assumption underlying the storage system was the reliability and adequacy of the water cooling infrastructure. Because radioactive decay generated substantial heat within the waste tanks, sufficient to raise temperatures to dangerous levels within days if cooling failed. Each tank was equipped with cooling coils connected to a central water circulation system. The designers calculated that this cooling system could maintain waste temperatures at safe levels indefinitely, provided normal maintenance and operation. However, this calculation embedded several critical assumptions that would later prove false. First, the design assumed that cooling system maintenance could be performed with the same reliability standards applied to conventional industrial equipment. Second, it assumed that cooling system failures would be immediately detectable and rapidly repairable. Third, it assumed that the chemical stability of the acetate waste would be maintained as long as temperatures remained below boiling point. Each of these assumptions would prove incorrect under operational conditions. The instrumentation and monitoring systems reflected these same philosophical limitations. Temperature monitoring within the tanks was minimal and discontinuous. No automatic alarm systems existed to alert operators to cooling system malfunctions. No backup cooling systems were installed. The design philosophy treated the storage tanks as passive containment vessels rather than active chemical reactors requiring continuous process control. This approach contrasted sharply with contemporary Western practice, where high-level waste storage was recognized as a complex chemical engineering problem, requiring sophisticated monitoring and control systems. American facilities operating under the Purex process stored waste that was chemically stable and generated less heat per unit volume. British facilities incorporated multiple redundant cooling systems and continuous temperature monitoring. The Soviet acetate waste, by contrast, represented a fundamentally more hazardous material being managed with less sophisticated engineering controls. The organizational structure at MAEAC further amplified these technical vulnerabilities. The facility operated under the Ministry of Medium Machine Building, a secretive organization that prioritized production targets above safety considerations. Technical staff understood the chemical hazards associated with acetate waste, but institutional pressure discouraged raising concerns that might delay production schedules. Maintenance activities were subordinated to production requirements, creating conditions where cooling system repairs could be deferred to avoid production interruptions. The training and procedural framework reflected this same production-focused mentality. Operators received extensive instruction in plutonium separation chemistry and production optimization, but minimal training in waste management safety procedures. No formal procedures existed for responding to cooling system failures. No emergency protocols addressed the possibility of chemical reactions within storage tanks. The institutional assumption was that waste storage represented a solved engineering problem requiring only routine maintenance attention. Contemporary documentation from the MAEAC facility reveals the extent to which safety considerations were treated as secondary to production objectives. Engineering reports focused almost exclusively on production efficiency and plutonium yield optimization. Safety analyses, when conducted at all, addressed radiological exposure risks for workers rather than potential accidents involving stored waste. The possibility of chemical explosions within storage tanks was not formally analyzed or addressed in facility safety documentation. The physical chemistry underlying the acetate waste created inherent instabilities that were poorly understood at the time. Unlike the nitrate waste produced by Western reprocessing methods, acetate waste contained organic compounds that could undergo exothermic decomposition at elevated temperatures. When combined with ammonium nitrate, these acetate compounds created a mixture comparable to industrial explosives. Temperature increases caused by cooling system failure would initiate a cascade of chemical reactions. Water evaporation would concentrate the waste, increasing both radioactivity and chemical reactivity. Higher temperatures would accelerate acetate decomposition, and the resulting chemical environment would become increasingly unstable until explosive decomposition became inevitable. The underground tank design, intended to provide containment and shielding, actually worsened these chemical hazards by creating an enclosed environment where pressure could build rapidly during explosive decomposition. The 8.2-meter depth made emergency intervention extremely difficult once chemical reactions began. The concrete canyon configuration focused explosive forces upward, ensuring that any explosion would breach containment and release radioactive material to the atmosphere. Soviet engineers possessed the theoretical knowledge to recognize these hazards, but institutional and political pressures prevented comprehensive safety analysis. The urgency of weapons production, combined with the secretive nature of the program, created an environment where raising safety concerns could be interpreted as questioning national security priorities. Technical staff understood that cooling system failure would be dangerous, but the specific mechanisms and timescales of potential accidents were never formally analyzed. The international isolation of the Soviet nuclear program further compounded these problems. Western nuclear facilities, despite their own safety limitations, benefited from technical exchange and peer review within the nascent nuclear engineering community. Soviet facilities operated in complete secrecy, preventing external technical review or comparison with international best practices. This isolation meant that design assumptions could not be validated against external experience or expertise. By 1957, the MAEAC storage facility had operated for 4 years without major incident, creating a false sense of confidence in the adequacy of existing safety systems. The absence of previous accidents was interpreted as validation of the design approach rather than evidence of accumulated risk. This institutional complacency, combined with the inherent chemical instabilities of acetate waste, created conditions where catastrophic failure would be triggered by any significant cooling system malfunction. The stage was thus set for disaster through a convergence of technical and institutional factors: chemically unstable waste stored in inadequately monitored tanks, cooling systems designed without redundancy or comprehensive maintenance protocols, and an organizational culture that subordinated safety analysis to production objectives. The specific triggering event, cooling system failure in tank number 7, would prove to be merely the final step in a failure sequence that had been years in the making. The cooling system failure that would trigger the Kyshtym explosion did not occur suddenly on September 29, 1957. Instead, it represented the culmination of systematic maintenance deficiencies and institutional blind spots that had accumulated over months or possibly years of operation. The documentary evidence reveals a facility where critical safety systems were treated as operational conveniences rather than life safety equipment, where maintenance procedures prioritized production continuity over equipment reliability, and where the information necessary to prevent catastrophic failure was either not collected or not acted upon. The maintenance culture at MIAC reflected the broader Soviet industrial philosophy of the 1950s, where production targets took absolute precedence over equipment longevity or safety margins. This approach, while potentially acceptable for conventional industrial operations, proved catastrophically inappropriate for managing high-level radioactive waste storage systems. The cooling infrastructure supporting the underground storage tanks represented a single point of failure for each tank, yet maintenance records indicate that cooling system reliability was not treated as a critical safety parameter. The specific cooling system that failed in Tank 7 consisted of water circulation coils designed to remove decay heat from the stored waste. This system required continuous operation to prevent dangerous temperature increases, yet no backup cooling capability existed. When maintenance was required on cooling system components, operators had no alternative means of heat removal available. This design philosophy assumed that all cooling system maintenance could be completed rapidly enough to prevent significant temperature increases, an assumption that proved incorrect under actual operating conditions. The institutional framework governing maintenance activities created multiple opportunities for cooling system degradation to go undetected. Maintenance scheduling was primarily driven by production requirements rather than equipment condition monitoring. Critical cooling system components could be removed from service to accommodate production activities, with repairs deferred until production schedules permitted. This approach treated cooling system availability as a convenience rather than a necessity, fundamentally misunderstanding the thermal dynamics of high-level radioactive waste storage. Personnel training programs further compounded these institutional weaknesses by focusing almost exclusively on production chemistry rather than waste management safety. Operators received extensive instruction in plutonium separation techniques, chemical purification methods, and production optimization procedures. However, training in waste storage thermal management, cooling system maintenance requirements, and emergency response procedures was minimal or non-existent. This training bias created a workforce that understood production processes in detail but lacked comprehensive knowledge of waste storage safety systems. The organizational structure at MIAC created additional barriers to effective safety management. Technical staff responsible for waste storage systems reported through a management hierarchy that prioritized production metrics over safety performance indicators. Maintenance supervisors were evaluated primarily on their ability to minimize production disruptions rather than their success in maintaining critical safety systems. This incentive structure actively discouraged maintenance activities that might interrupt production, even when such activities were necessary to ensure safe operation. Communication protocols within the facility further amplified these organizational problems. No formal procedures existed for reporting cooling system degradation or malfunction to senior management. Technical staff who identified potential problems with waste storage systems had limited channels for escalating concerns outside the immediate maintenance hierarchy. The secretive nature of the facility's operations meant that external technical consultation was impossible, preventing independent review of maintenance practices or safety procedures. The documentation available from the MIAC facility reveals that cooling system reliability problems were recognized by technical staff well before the September 1957 explosion. Maintenance logs indicate recurring problems with cooling water circulation, temperature control, and equipment reliability. However, these technical concerns were not translated into systematic corrective actions or design improvements. Instead, cooling system problems were treated as routine maintenance issues to be addressed when production schedules permitted. The specific failure mode that affected Tank 7 appears to have involved gradual degradation of cooling system effectiveness rather than sudden catastrophic failure. Temperature monitoring data, where available, suggests that heat removal capacity decreased over time as cooling system components failed or became fouled. This gradual degradation would have been detectable through systematic temperature monitoring, but the facility lacked comprehensive instrumentation to track thermal conditions within storage tanks. The human factors implications of this institutional framework were profound and predictable. Operators working within a system that prioritized production over safety would naturally focus their attention on production-related parameters rather than waste storage conditions. When cooling system problems occurred, operators would be inclined to implement temporary fixes that minimized production disruption, rather than comprehensive repairs that ensured long-term reliability. This behavioral pattern, while rational within the institutional context, systematically undermined the safety systems required to prevent waste storage accidents. The technical knowledge existed within the MIAC organization to recognize and prevent cooling system failure, but institutional barriers prevented this knowledge from being effectively applied. Engineers understood that cooling system reliability was critical for safe waste storage, but lacked the organizational authority to implement necessary improvements. Maintenance technicians could identify cooling system degradation, but lacked procedures for escalating safety concerns. Operators could recognize abnormal thermal conditions, but lacked both instrumentation and training to respond appropriately. The acetate waste storage system design further exacerbated these human factors problems by creating extended time delays between cooling system failure and observable consequences. Unlike systems where failure modes are immediately apparent, cooling system degradation in waste storage tanks could continue for weeks or months before reaching dangerous conditions. This delay created a false sense of security, allowing operators to defer maintenance activities without immediately obvious consequences. The institutional assumption that waste storage represented a solved engineering problem prevented systematic analysis of potential failure modes or development of appropriate emergency procedures. No formal risk assessments were conducted to identify critical system vulnerabilities. No emergency response plans existed to address cooling system failure scenarios. No backup systems were designed or installed to provide alternative heat removal capability. This systematic neglect of safety analysis meant that when cooling system failure did occur, operators had no procedural framework for responding effectively. Contemporary Soviet industrial practices provided additional context for understanding these institutional failures. The planned economy system of the 1950s emphasized production quantity over quality or safety, creating systemic pressures that discouraged activities that might reduce short-term output. This economic framework was particularly problematic for nuclear facilities, where safety margins were critical and where accidents could have catastrophic consequences extending far beyond the immediate facility. The geographical isolation of the MIAC facility compounded these institutional problems by preventing external technical review or comparison with international best practices. Western nuclear facilities, despite their own limitations, benefited from technical exchange within the emerging nuclear engineering community. Soviet facilities operated in complete isolation, preventing validation of design assumptions or operational procedures against external experience. The secrecy requirements governing MIAC operations created additional barriers to effective safety management. Technical staff were prohibited from discussing operational problems with colleagues outside the immediate organization, preventing informal knowledge transfer that might have identified potential solutions. Academic collaboration was impossible, preventing access to broader scientific expertise that might have improved understanding of acetate waste chemistry or thermal management requirements. Training deficiencies extended beyond technical knowledge to include fundamental safety culture concepts. Operators were not taught to question design assumptions or to identify potential failure modes that had not been previously encountered. The institutional expectation was that existing procedures and systems were adequate for all foreseeable conditions, discouraging the kind of critical thinking that might have identified emerging safety problems. The maintenance infrastructure at MEAC reflected these same institutional limitations. Spare parts for cooling system components were often unavailable or delayed, forcing operators to implement temporary repairs that compromised system reliability. Maintenance tools and equipment were frequently inadequate for performing comprehensive repairs, leading to partial fixes that addressed immediate symptoms rather than underlying problems. Quality control procedures for maintenance activities were minimal, preventing systematic verification that repairs had restored full system capability. By mid-1957, the combination of these institutional factors had created conditions where cooling system failure in one or more storage tanks was highly probable. The systematic neglect of maintenance requirements, combined with the absence of backup systems and emergency procedures, ensured that any significant cooling system malfunction would progress rapidly toward catastrophic failure. The specific failure that occurred in Tank 7 was thus not an isolated equipment malfunction, but rather the predictable result of systematic institutional dysfunction that had undermined the safety systems required for safe waste storage operation. The cooling system failure that initiated the Kyshtym disaster began not on September 29, 1957, but weeks or possibly months earlier, as a gradual degradation that remained invisible to operators until intervention became impossible. The available evidence suggests that Tank 7's cooling system experienced progressive failure, with heat removal capacity declining incrementally while waste temperatures increased along a trajectory that would inevitably lead to explosive decomposition. This progressive failure exemplifies how complex technical systems can drift toward catastrophic states while appearing to function normally according to available instrumentation. The thermal dynamics governing high-level acetate waste storage created inherently unstable conditions that required continuous active management. The radioactive decay occurring within Tank 7 generated approximately 15 to 20 kilowatts of thermal energy continuously, equivalent to running 15 electric space heaters inside a sealed container. Without effective heat removal, this energy input would raise waste temperatures at a rate of several degrees per day, initiating a cascade of chemical and physical changes that would progressively worsen thermal management requirements. The cooling water circulation system designed to manage this thermal load operated on principles similar to conventional industrial process cooling. But the consequences of failure were fundamentally different. In typical industrial applications, cooling system failure might result in reduced production efficiency or equipment damage, costly but not catastrophic outcomes. In the context of high-level radioactive waste storage, cooling system failure initiated irreversible physical and chemical changes that would progress inexorably toward explosive conditions. The specific failure mode affecting Tank 7's cooling system appears to have involved either pump malfunction, circulation line blockage, or heat exchanger fouling, any of which would reduce cooling water flow rate and compromise heat removal capability. Contemporary maintenance documentation indicates that such problems were recurring issues throughout the storage facility, typically addressed through temporary repairs or workarounds that restored partial function without fully correcting underlying problems. The institutional pressure to minimize production disruptions meant that comprehensive cooling system repairs were often deferred in favor of expedient fixes that maintained minimal functionality. As cooling effectiveness decreased, the thermal conditions within Tank 7 began changing in ways that were not immediately detectable through available instrumentation. Temperature monitoring within the storage tanks was sporadic and inadequate, providing operators with little information about actual thermal conditions. The underground location of the tanks made direct observation impossible, while the radioactive environment prevented close approach for detailed inspection. Operators thus had limited ability to detect progressive cooling system degradation until thermal conditions had already progressed well beyond safe operating parameters. The chemical composition of acetate waste created particularly dangerous thermal feedback mechanisms that were poorly understood at the time of the accident. As temperatures increased due to inadequate cooling, water within the waste began evaporating at accelerated rates, concentrating the remaining solution and increasing both radioactivity and chemical reactivity per unit volume. This concentration effect amplified heat generation rates while simultaneously reducing the thermal capacity of the waste to absorb additional heat input. The result was a positive feedback loop where declining cooling effectiveness led to conditions that required even more effective cooling to maintain stability. The timeline of thermal progression within Tank 7 can be reconstructed from post-accident analysis and contemporary understanding of acetate waste chemistry. Initial cooling degradation would have caused waste temperatures to rise from normal operating levels around 30–40 degrees Celsius toward 100 degrees Celsius over a period of weeks. As temperatures approached the boiling point of water, evaporation rates would have increased dramatically, accelerating the concentration process and further raising temperatures. Once temperatures exceeded 100 degrees Celsius, chemical decomposition of acetate compounds would have begun, generating additional heat and creating increasingly volatile chemical conditions. The critical threshold for irreversible progression toward explosive conditions occurred when waste temperatures reached approximately 150 degrees Celsius, initiating rapid decomposition of ammonium nitrate compounds within the concentrated waste. At this point, the chemical reactions generating heat exceeded the maximum possible cooling capacity of the degraded cooling system, ensuring that temperatures would continue rising regardless of any cooling system repairs that might be attempted. This thermal runaway condition represented the point of no return, beyond which explosive decomposition became inevitable even if operators recognized the problem and attempted corrective action. The institutional framework governing facility operations prevented effective response even if thermal problems had been detected earlier in the progression. No emergency procedures existed for addressing cooling system failures in waste storage tanks. No backup cooling systems were available to provide alternative heat removal. No provisions existed for emergency waste removal or transfer to alternative storage. The facility design assumed that cooling system reliability could be maintained through routine maintenance, providing no contingency options for scenarios where primary cooling systems failed completely. Operators working at MAAC during this period had no indication that catastrophic conditions were developing within Tank 7. The gradual nature of cooling system degradation meant that any observable changes in facility operations would have appeared routine rather than alarming. Cooling water flow rates might have decreased slightly, but such variations were common and typically attributed to routine maintenance issues rather than impending system failure. Temperature monitoring, where available, would have shown gradual increases that might have been attributed to seasonal variations or measurement uncertainty rather than systematic cooling failure. The physical chemistry occurring within Tank 7 during this progression created conditions that had never been previously encountered or studied in detail. The combination of high-level radioactive materials, concentrated ammonium nitrate solutions, and organic acetate compounds under elevated temperatures represented a novel chemical environment with poorly understood reaction kinetics. Soviet engineers had theoretical knowledge of the individual components, but lacked experimental data on the behavior of these materials under the specific conditions developing within the storage tank. Contemporary documentation suggests that some technical staff may have recognized potential problems with waste storage thermal management but lacked both the instrumentation and institutional authority necessary to investigate further. Engineering reports from the period reference concerns about cooling system reliability and waste storage safety, but these concerns were not translated into systematic investigation or corrective action. The institutional culture prioritized production operations over waste management activities, ensuring that potential safety concerns received minimal attention unless they directly impacted production capabilities. The progression from initial cooling degradation to explosive conditions probably occurred over a time frame of 6 to 12 weeks, representing an extended period during which intervention might have been possible if appropriate monitoring and response capabilities had existed. However, the combination of inadequate instrumentation, institutional inattention to waste storage safety, and absence of emergency response procedures ensured that this progression would continue undetected until explosion became inevitable. The chemical environment within Tank 7 during the final weeks before explosion represented conditions of extreme instability that were unprecedented in nuclear facility operations. Waste temperatures had progressed well beyond design parameters. Chemical decomposition was generating additional heat and gas pressure, and the structural integrity of the tank itself was being compromised by thermal expansion and chemical corrosion. The underground location that was intended to provide containment had become a confined pressure vessel where explosive forces could build to catastrophic levels. By early September 1957, the conditions within Tank 7 had progressed beyond any possibility of intervention or stabilization. Waste temperatures had reached levels where rapid chemical decomposition was generating heat faster than any conceivable cooling system could remove it. Gas generation from chemical reactions was creating pressure buildup that would inevitably breach tank containment. The specific trigger for the explosion, whether thermal runaway, chemical decomposition, or pressure failure, became irrelevant as multiple failure mechanisms converged toward the same catastrophic outcome. The final days before the explosion represented a period when the facility continued normal operations while hosting an increasingly unstable chemical reactor that was progressing inexorably toward explosive release. Operators performed routine duties, production systems functioned normally, and institutional attention remained focused on production targets rather than waste storage safety. The absence of adequate monitoring systems meant that the developing catastrophe remained invisible until the moment of explosion, when 70 to 100 tons of TNT equivalent energy was released in an instant that had been months in the making. At 4:22 p.m. on September 29, 1957, the chemical and physical processes that had been building within Tank 7 for months reached their inevitable conclusion. The explosion that destroyed the storage tank and contaminated vast areas of Soviet territory was not a sudden catastrophic failure, but rather the predictable endpoint of a complex sequence of chemical reactions, thermal dynamics, and structural failures that had been progressing, in accordance with well-understood physical principles. The physics of this disaster reveal how fundamental chemistry and thermodynamics, when left unchecked by adequate engineering controls, can generate destructive forces comparable to conventional explosives. The immediate cause of the explosion was the rapid decomposition of ammonium nitrate that had been concentrated through weeks of water evaporation within the overheated waste. Ammonium nitrate, widely used in mining explosives and agricultural fertilizers, becomes increasingly unstable as temperature and concentration increase. At the temperatures that had developed within Tank 7, estimated to exceed 350 degrees Celsius, ammonium nitrate undergoes rapid exothermic decomposition, releasing nitrogen oxides, water vapor, and oxygen while generating substantial heat and gas volume expansion. The chemical equation governing this decomposition process is deceptively simple: NH4NO3 N2O plus 2H2O plus heat. However, the practical implications of this reaction occurring within a confined space containing hundreds of tons of concentrated radioactive waste were catastrophic. The decomposition released approximately 1,500 kilojoules of energy per kilogram of ammonium nitrate, while simultaneously generating gas volumes approximately 1,000 times greater than the original solid material. Within the confined space of the underground storage tank, this combination of energy release and gas generation created explosive pressures that no containment system could withstand. The presence of organic acetate compounds within the waste amplified these explosive effects through additional chemical reactions that were poorly understood at the time of the accident. Acetate compounds, when heated to decomposition temperatures, generate acetic acid vapors, carbon dioxide, and various organic fragments that can participate in secondary combustion reactions. These organic materials effectively served as additional fuel for the explosion, increasing both the energy release and the complexity of the chemical environment during the explosive event. The thermal progression leading to explosion followed predictable thermodynamic principles that should have been foreseeable through proper engineering analysis. As cooling system effectiveness declined, the waste temperature increased according to a heat balance equation where thermal input from radioactive decay exceeded heat removal through the degraded cooling system. The rate of temperature increase accelerated as water evaporation concentrated the waste, reducing thermal capacity while maintaining constant heat input from radioactive sources. The critical temperature threshold where explosive decomposition became inevitable was reached when waste temperatures exceeded approximately 210 degrees Celsius, the point at which ammonium nitrate begins rapid decomposition under confined conditions. Once this threshold was crossed, the chemical reactions generating heat exceeded any possible external cooling capacity, ensuring that temperatures would continue rising toward explosive conditions regardless of any attempted intervention. This thermal runaway represented a classic positive feedback system where the effects of the disturbance amplified the disturbance itself. The pressure dynamics within Tank 7 during the final moments before explosion can be calculated using standard chemical engineering principles. As ammonium nitrate decomposition accelerated, gas generation rates increased exponentially according to Arrhenius kinetics, where reaction rates double approximately every 10 degrees Celsius of temperature increase. The confined volume of the underground tank prevented pressure relief, causing gas pressures to build toward the structural limits of the containment system. The explosion itself occurred when internal pressure exceeded the structural capacity of either the tank walls or the concrete lid system. Contemporary estimates suggest that gas pressures reached levels equivalent to 50 to 100 atmospheres before structural failure occurred, releasing the accumulated energy in a fraction of a second. The force of this pressure release was estimated at 70 to 100 tons of TNT equivalent, sufficient to lift the 160-ton concrete lid and destroy buildings 200 meters from the explosion site. The radioactive material release mechanism during the explosion involved complex fluid dynamics and particle dispersion processes that were unprecedented in nuclear facility experience. As the tank ruptured and explosive gases expanded, liquid waste was converted to aerosol droplets and solid particles that were carried aloft by the rising column of hot gases. Approximately 10% of the total radioactive inventory within the tank, roughly 2 million curies, was dispersed into the atmosphere, while the remaining 90% was deposited in the immediate vicinity of the explosion or remained within the damaged storage facility. The particle size distribution of dispersed radioactive material determined the extent of atmospheric transport and ground contamination patterns. Larger particles and droplets settled quickly near the explosion site, contributing to intense local contamination that made immediate area access impossible. Smaller particles remained airborne for extended periods, allowing atmospheric transport over hundreds of kilometers before deposition. The specific particle size distribution was determined by the explosive forces and thermal conditions during the release, creating a contamination pattern that extended far beyond the immediate facility boundaries. The chemical composition of the released material reflected the complex chemistry occurring within the storage tank during the months preceding explosion. The released material contained not only the original radioactive isotopes from plutonium production waste, but also the chemical products of thermal decomposition reactions that had occurred during the overheating process. This chemical complexity created contamination with different physical and chemical properties than had been previously encountered in nuclear facility operations, complicating both immediate response efforts and long-term remediation activities. The isotopic composition of released radioactivity was dominated by strontium-90 and cesium-137, long-lived fission products that had accumulated during plutonium production operations. These isotopes had half-lives of approximately 30 years, ensuring that contamination would persist for decades after the explosion. The biological impact of these specific isotopes was particularly severe because strontium-90 concentrates in bone tissue, while cesium-137 distributes throughout soft tissues, creating long-term internal radiation exposure for affected populations. The atmospheric dispersion of radioactive material followed meteorological patterns that were typical for the region but unfortunate in terms of population exposure. Prevailing wind patterns carried the radioactive plume northeast from the explosion site, passing over populated rural areas, rather than the less populated regions to the south or west. The combination of atmospheric stability conditions and moderate wind speeds created optimal conditions for long-distance transport while maintaining sufficient concentration to cause significant ground contamination over an extended area. The thermal effects of the explosion extended beyond the immediate chemical decomposition to include secondary heating effects that complicated emergency response efforts. The explosion generated intense thermal radiation that ignited combustible materials near the blast site, while residual radioactive material continued generating decay heat that elevated temperatures in contaminated areas for weeks after the initial event. These thermal effects created access restrictions that delayed emergency response and complicated efforts to assess the extent of radioactive contamination. The structural damage caused by the explosion revealed the magnitude of forces generated by ammonium nitrate decomposition under confined conditions. The complete destruction of the concrete lid, a structure weighing 160 tons and designed to withstand substantial structural loads, demonstrated explosive forces comparable to conventional munitions. The damage pattern extending 200 meters from the explosion site indicated blast pressures sufficient to destroy unreinforced masonry construction and cause significant damage to reinforced concrete structures. The timing of the explosion, occurring on a Sunday afternoon when most facility personnel were off duty, was purely coincidental but significantly affected both the immediate human impact and the institutional response to the accident. The reduced staffing levels meant that fewer people were immediately exposed to radiation from the explosion, but also meant that fewer technical personnel were immediately available to assess the situation and initiate emergency response procedures. This timing delay contributed to the extended period before the full scope of the accident was recognized, and appropriate response measures were implemented. The explosion marked the end of the thermal and chemical progression that had been building within Tank 7 for months, but it also marked the beginning of a much larger and longer-lasting contamination problem that would affect hundreds of thousands of people over multiple decades. The instantaneous release of energy that had been accumulating through radioactive decay and chemical instability transformed a localized waste storage problem into a regional environmental disaster, with consequences that extended far beyond the immediate facility boundaries. The explosion that destroyed Tank 7 at 4:22 p.m. on September 29, 1957 marked not the conclusion of the Kyshtym disaster, but rather the beginning of a protracted crisis that would test the institutional capacity of the Soviet nuclear program to respond to unprecedented contamination conditions. The immediate aftermath of the explosion presented facility management with a complex array of technical challenges that had never been previously encountered. Massive radioactive contamination of industrial facilities, atmospheric dispersion of unknown scope and duration, and the fundamental question of whether continued plutonium production operations could be maintained in a contaminated environment. The initial response to the explosion was shaped by the institutional culture that had contributed to the accident itself. The facility's operational priority remained plutonium production for the Soviet weapons program, creating pressure to minimize disruptions that might affect production schedules. This institutional bias influenced every aspect of the emergency response, from the assessment of contamination extent to the development of protective measures for personnel. The result was a response strategy that prioritized operational continuity over comprehensive safety analysis, the same philosophical approach that had enabled the original accident to occur. The immediate physical evidence of the explosion was unmistakable. The concrete lid of Tank 7 had been completely destroyed, radioactive debris was scattered across the facility site, and radiation monitoring instruments throughout the complex were registering readings far above normal background levels. However, translating these observations into an understanding of the overall situation proved extremely difficult due to limitations in both monitoring equipment and institutional experience with large-scale contamination events. The radiation monitoring systems available at MIAC in 1957 were designed for routine operational monitoring rather than emergency response to major contamination incidents. Most monitoring instruments had measurement ranges that were quickly exceeded by the intense radiation fields created by dispersed radioactive material. Portable survey instruments became saturated and unusable in heavily contaminated areas, while fixed monitoring stations either failed due to radiation damage or were rendered inaccessible by contamination levels. This instrumentation failure meant that emergency responders lacked reliable information about contamination distribution and intensity during the critical first hours after the explosion. The institutional secrecy requirements governing all MAOC operations created additional complications for emergency response efforts. Standard industrial emergency response procedures would have involved immediate notification of external emergency services, coordination with regional health authorities, and possibly evacuation of nearby population centers. However, the classified nature of the facility prevented any external communication about the accident, forcing facility management to develop emergency response capabilities entirely from internal resources. The contamination pattern created by the explosion presented unprecedented technical challenges for both immediate response and long-term facility operations. Radioactive material had been distributed throughout critical production areas, contaminating equipment, structures, and transportation systems essential for plutonium production operations. The intensity of contamination in some areas was sufficient to prevent access by personnel, even with protective equipment, effectively rendering portions of the facility inoperable until contamination levels decreased through natural decay. The decision-making process during the first 24 hours after the explosion reflected the institutional priorities that had shaped facility operations since construction. Rather than implementing comprehensive emergency response procedures, which did not exist, facility management focused on maintaining production operations to the maximum extent possible, while implementing minimal protective measures for personnel. This approach treated the accident as an operational disruption to be managed, rather than a safety emergency requiring fundamental changes in facility operations. The transportation of radioactive contamination beyond the immediate explosion site occurred through mechanisms that were initially not recognized or understood by facility personnel. Vehicles traveling through contaminated areas carried radioactive material on wheels and chassis, spreading contamination along roadways and into previously clean areas. Personnel working in contaminated zones carried radioactive material on clothing and equipment, transporting contamination into administrative areas, cafeterias, and residential zones within the facility complex. The recognition that contamination was spreading beyond the immediate explosion site led to the implementation of basic contamination control measures approximately 6 to 8 hours after the explosion. These measures included establishment of contamination control checkpoints, requirements for protective clothing in designated areas, and restrictions on vehicle movement between contaminated and clean zones. However, these control measures were implemented after substantial contamination spread had already occurred, limiting their effectiveness in preventing further dispersal. The assessment of atmospheric contamination proved particularly challenging due to limitations in both monitoring capabilities and meteorological understanding. The facility lacked comprehensive atmospheric monitoring systems that could track the movement and concentration of airborne radioactive material over extended areas. Weather data was limited to basic wind direction and speed measurements, preventing detailed analysis of atmospheric dispersion patterns or prediction of contamination deposition areas. The discovery that radioactive contamination extended far beyond the facility boundaries occurred gradually over the first week following the explosion, as radiation monitoring teams began surveying areas progressively farther from the explosion site. These surveys revealed a contamination plume extending northeast from MAOC over a distance of hundreds of kilometers, with contamination levels in some areas sufficient to pose significant health risks to exposed populations. This discovery fundamentally changed the nature of the emergency from a facility accident to a regional contamination event. The institutional response to evidence of widespread contamination reflected the broader Soviet political context of the late 1950s. Acknowledging the extent of contamination would have required admitting that a major accident had occurred at a highly classified facility. potentially revealing sensitive information about Soviet nuclear weapons production capabilities. The decision was made to classify all information related to the accident and to manage the contamination problem through internal resources without external assistance or acknowledgement. The technical challenges of managing contamination over such an extended area were unprecedented in nuclear facility experience. Standard decontamination techniques were adequate for small-scale contamination incidents involving limited areas and materials, but were completely inadequate for addressing contamination distributed over thousands of square kilometers. The logistics of providing protective equipment, monitoring services, and decontamination capabilities for such an extensive area exceeded the resources available to the facility organization. The development of evacuation criteria and procedures occurred through ad hoc decision-making rather than pre-established emergency planning. No formal procedures existed for determining when contamination levels warranted population evacuation, what protective measures should be implemented for evacuated populations, or how evacuation operations should be coordinated and implemented. These fundamental emergency response capabilities had to be developed in real time while managing an ongoing contamination crisis. The establishment of the 90 SR contamination threshold of 2CI, KM2, as the evacuation criterion represented a pragmatic engineering decision rather than a scientifically optimized health protection standard. This criterion was based on available radiation monitoring capabilities, logistical constraints on evacuation operations, and political considerations related to minimizing the apparent scope of the accident. The scientific basis for this particular threshold was limited, reflecting the absence of comprehensive health effects data for chronic exposure to environmental strontium 90% contamination. The evacuation operations that began approximately 1 week after the explosion faced significant logistical and political challenges. The affected population had no prior knowledge of the Mayak facility or its potential hazards, making it difficult to explain the necessity for evacuation without revealing classified information about nuclear weapons production. The evacuation process was therefore presented as a routine resettlement program rather than an emergency response to radioactive contamination, creating confusion and resistance among affected populations. The long-term management strategy that emerged from the first months after the explosion reflected institutional priorities that continued to emphasize production continuity over comprehensive contamination remediation. Areas with contamination levels below the evacuation threshold were designated for continued agricultural and residential use, despite limited understanding of long-term health effects from chronic low-level radiation exposure. This approach minimized the apparent scope of the accident while accepting uncertain health risks for affected populations. The technical lessons learned during the stabilization period revealed fundamental inadequacies in both facility design and institutional preparedness for managing major contamination events. The absence of backup cooling systems, comprehensive monitoring capabilities, emergency response procedures, and external coordination mechanisms had transformed what should have been a manageable facility incident into a regional disaster. These lessons would later influence Soviet nuclear facility design and emergency planning, but the immediate priority remained maintaining operational secrecy while minimizing acknowledged impacts. The stabilization of facility operations during the months following the explosion required developing new operational procedures for working in contaminated environments, implementing enhanced monitoring and protective measures, and maintaining production capabilities despite significant contamination of critical facility areas. This stabilization process demonstrated both the resilience of the Soviet nuclear program and its willingness to accept substantial safety risks to maintain weapons production capabilities. The true magnitude and implications of the Kyshtym disaster only became apparent through decades of forensic investigation, environmental monitoring, and epidemiological research that gradually revealed the full scope of contamination and its lasting consequences. The systematic study of this accident, once Soviet secrecy barriers were eventually breached, provided unprecedented insights into the long-term behavior of environmental radioactive contamination and the institutional factors that enable preventable disasters to occur in complex technical systems. The forensic reconstruction of the accident mechanism, conducted primarily after 1989 when Soviet authorities finally acknowledged the event, confirmed the chemical explosion hypothesis, and validated theoretical predictions about ammonium nitrate decomposition under the thermal conditions that had developed within Tank 7. Detailed chemical analysis of residual waste materials and explosion debris demonstrated that the explosive force had indeed resulted from rapid ammonium nitrate decomposition amplified by organic acetate compounds, generating the 70 to 100 TNT equivalent energy release estimated from structural damage patterns. The comprehensive mapping of radioactive contamination, accomplished through extensive soil sampling and environmental monitoring programs, revealed the East Ural Radioactive Trace, URT, as a contamination pattern extending over 23,000 square kilometers with varying intensity levels. This contamination distribution validated atmospheric dispersion models and demonstrated how a single facility accident could create environmental impacts extending across multiple administrative regions and affecting hundreds of thousands of people over multiple decades. The isotopic composition analysis of environmental contamination provided critical insights into the waste chemistry and explosion dynamics that had not been available during the immediate response period. The predominance of strontium-90 and cesium-137 in environmental samples confirmed that the explosion had involved high-level waste from plutonium production operations, while the presence of specific isotopic ratios allowed forensic reconstruction of the original waste composition and the chemical processes occurring during the thermal progression leading to explosion. Long-term environmental monitoring revealed the persistence and mobility of radioactive contamination under various environmental conditions, providing data on contamination behavior that had significant implications for nuclear waste management practices worldwide. Studies of contamination migration through soil profiles, uptake by vegetation, and concentration in aquatic ecosystems demonstrated the complex pathways through which radioactive material could continue affecting human populations, decades after the original release. The epidemiological studies conducted on populations exposed to URT contamination provided some of the first comprehensive data on health effects from chronic exposure to environmental radioactive contamination. These studies, initiated in the 1960s but not published until the 1990s, demonstrated statistically significant increases in leukemia and solid cancer rates among exposed populations, with risk levels correlating with estimated radiation dose levels. The estimated excess cancer deaths, 49 to 55 cases above background rates, represented measurable health impacts from what had been initially characterized as a minor facility incident. The detailed analysis of institutional factors contributing to the accident revealed systematic patterns that extended far beyond the specific circumstances at MIAC. The subordination of safety analysis to production objectives, the absence of independent safety review mechanisms, and the prevention of external technical consultation created conditions where preventable accidents became inevitable over extended operational periods. These institutional patterns were subsequently identified in multiple other Soviet nuclear facilities, suggesting systemic rather than isolated problems. The investigation of cooling system failure mechanisms provided crucial technical insights that influenced nuclear waste storage design practices worldwide. The analysis confirmed that cooling system reliability was indeed the critical safety parameter for high-level waste storage, validating the need for redundant cooling systems, comprehensive temperature monitoring, and emergency backup cooling capabilities. These lessons were incorporated into international nuclear waste management standards and influenced facility design practices in multiple countries. The examination of emergency response capabilities during the immediate aftermath of the explosion revealed fundamental inadequacies in institutional preparedness for managing large-scale contamination events. The absence of pre-established evacuation criteria, external coordination mechanisms, and comprehensive monitoring capabilities had significantly amplified the human and environmental impacts of the original accident. These lessons contributed to the development of international emergency response standards and cross-border coordination agreements for nuclear accidents. The analysis of evacuation decision-making processes demonstrated how political and institutional considerations could override health protection objectives even during emergency conditions. The delayed implementation of evacuations, with some populations not relocated until nearly 2 years after the accident, resulted in unnecessary radiation exposure that could have been prevented through earlier action. This analysis contributed to the development of more science-based evacuation criteria and pre-established decision-making frameworks for nuclear emergencies. The long-term agricultural and environmental impact studies provided detailed documentation of radioactive contamination, effects on ecosystem function, and food chain contamination pathways. These studies demonstrated how radioactive material could persist in agricultural systems for decades, requiring ongoing monitoring and management interventions to prevent unacceptable human exposure through food consumption. The data from these studies influenced international food safety standards and agricultural management practices in contaminated areas. The examination of secrecy policies and their impact on both accident causation and response effectiveness revealed the fundamental incompatibility between comprehensive safety management and operational secrecy requirements. The prevention of external technical review, the restriction of scientific publication, and the prohibition of international consultation had systematically undermined the technical capabilities required for safe nuclear facility operation. These findings contributed to later policy changes allowing increased transparency in nuclear safety matters. The forensic analysis of waste storage design philosophy revealed how the treatment of waste management as a secondary engineering problem had created systematic vulnerabilities throughout the Soviet nuclear complex. The acetate reprocessing method, the absence of backup cooling systems, and the inadequate monitoring capabilities reflected institutional priorities that viewed waste storage as a solved problem rather than an ongoing safety challenge requiring continuous engineering attention. The investigation of training and procedural adequacy demonstrated how production-focused training programs had systematically failed to prepare operators for waste storage safety management responsibilities. The emphasis on production chemistry rather than thermal management, the absence of emergency response training, and the lack of systematic safety analysis created a workforce that was technically competent in production operations but unprepared for safety-critical decision-making during emergency conditions. The analysis of maintenance culture and equipment reliability management revealed how production-focused performance metrics had systematically undermined the maintenance activities required for safe operation. The deferral of cooling system maintenance, the absence of reliability monitoring, and the treatment of safety systems as operational conveniences rather than life safety equipment created conditions where equipment failure progression toward catastrophic outcomes was predictable and preventable. The comprehensive review of design assumptions and safety analysis adequacy demonstrated how the absence of systematic risk assessment had prevented identification of credible accident scenarios and appropriate protective measures. The failure to analyze ammonium nitrate explosion potential, the absence of containment adequacy analysis, and the lack of atmospheric dispersion assessment created a facility design that was fundamentally inadequate for the hazards it was intended to manage. The international impact of Kyshtym findings on nuclear safety practices extended far beyond the Soviet Union, influencing reactor safety research, waste management practices, and emergency preparedness standards worldwide. The recognition that institutional factors could override technical safety systems led to enhanced emphasis on safety culture, independent oversight, and systematic risk assessment in nuclear facility operations globally. The legacy of the Kyshtym disaster in contemporary nuclear safety practice is visible in multiple areas of current industry standards and regulatory requirements. Defense in-depth principles now explicitly address institutional failure mechanisms, waste storage systems incorporate multiple redundant safety systems, and emergency preparedness standards require comprehensive planning for large-scale contamination events. The accident demonstrated that technical safety depends ultimately on institutional commitment to systematic safety analysis and continuous improvement rather than compliance with minimum standards. The broader lessons from Kyshtym extend beyond nuclear technology to encompass any complex technical system where institutional pressures might override safety requirements. The patterns of production pressure overriding safety analysis, secrecy preventing external review, and maintenance deferral creating latent failure conditions are recognizable in multiple industrial contexts where similar institutional dynamics could enable preventable disasters. The forensic analysis of this disaster ultimately confirmed that the explosion was not an accident in the traditional sense, but rather the inevitable result of systematic institutional failures that had undermined every technical barrier intended to prevent such events. The cooling system failure, the chemical explosion, and the massive contamination release were all predictable consequences of design assumptions, operational practices, and institutional priorities that treated safety as subordinate to production objectives. The true lesson of Kyshtym is not that nuclear technology is inherently dangerous, but that complex technical systems require institutional frameworks that prioritize safety analysis, encourage external review, and maintain safety systems with the same rigor applied to production operations.